The topic for this week is variable to block length coding. Last week we saw a block to variable length coding in which the input message is of fixed size, fixed length, and output message is of the output code words are of variable length. So by using the variable length code words, we were able to compress our message. But sometimes in some applications, we might not want to store variable length messages or variable length code words. For example, if you are storing something in a computer, then fixed bits or bytes are allocated for a particular code word or message or anything. So in that case, you would like to keep the code word length fixed, but if you still want to make the source coding efficient, then you would have to allow for variable length input messages. So you have a source parser which will collect a certain number of input symbols and declare that as a message. So each message can be of variable length. And once you have a message, a valid message, a single code word of fixed length is assigned to that message. So this week was about that type of coding, which is called variable to block length coding. And we also saw the asymptotic equipartition property. It says that so there are typical sets of uh, messages which are highly probable to occur when you have a sequence of random variables. A typical set of the possible outputs is highly likely, and if we do coding only for the messages in the typical set, then we can still get arbitrary low error probabilities, uh, and we can get a large compression. Or more importantly, if we allow lossy coding, then we can actually ignore the only messages which are not in the typical set, and uh, no need to employ complicated coding schemes for them. And we do coding only for the messages in the typical set, then uh, the typical set will be such a set with such that it will occur with a high probability, and each of the messages in the typical set occurs with is equally likely. And when you do coding for only those messages which are in the typical set, you usually need a much lesser number of bits to do coding than if you encoded every particular possible message. Uh, that's kind of the gist of asymptotic equipartition probability. Then we also saw block uh, coding and how in block to block coding the lossless version of it is not very interesting. But if you allow lossy encoding, then we can do some interesting things, even in block to block coding. As usual, we'll solve 10 questions this week, which will be similar to the questions you will get for this week's assignment, week 3 assignment. Which of the following is a proper message set? There are four options. I encourage you to solve this problem yourself. I'll come back in 2 minutes, 2 minutes and give you the solution. They're asking which of these is a proper message set. For that, we need to know what a proper message set is. So, a a proper message set for a k resource is a set of messages that form a complete set of leaves for a rooted k tree. So in these three options, in the first option, this root is left out, this leaf is left out, so it's not a complete set of leaves. So option 1 is ruled out. Similarly, option 2, you don't have a complete set of leaves. So that leaf that I have marked right now, that's not a message. So again, we don't have a complete set of leaves. In option D, we do have a complete set of leaves. But there's one more requirement. Uh, that is, so when we say complete set of leaves, it also means that uh, no message is a prefix of a longer message. So in option D, you can see that uh, 0 is a message and 1 is a message. So that would mean 0 is a prefix of this message 00. It's also prefix of the message 01. Similarly, 1 is a prefix of the message 10 and the message 11. So this again rules out the possibility that option D is a proper message set. So the right answer is option C. By a proper message set, why we need the idea of a proper message set is that when you are collecting, when you are parsing the information source, then we are considering a discrete memory resource here. When you are parsing symbols from the source, uh, for any possible sequence of source symbols, you should be able to split that up into messages. So, uh, any sufficient length sequence from the source must have a message as its prefix. Otherwise, if you have something like this as a message set, so this is A, B, C, A, B, C. Now, A, B, C, A, and C, B are messages, but suppose, but C, C is not a is not uh, included in your message set. Then what happens is, if your source emits with a non-zero probability, it can emit a sequence containing only C's, and then you'll never be able to, uh, g no matter what length parser you use, you'll never be able to get one of your messages uh, out of this information sequence. So it's all right if your message is a long message, which your message set contains a very long message, such that uh, your information source has to transmit a lot of information symbols, and then only you collect them and then you get a proper message. But in a finite number of symbols, once your source starts uh, transmitting symbols within a finite length, you should be able to identify a message from your message set. Your message set should be such that uh, no matter what information sequence is actually transmitted, then you will you will be able to split that up into uh, messages in your message set. That's why you need a full set of leaves. And the second thing is that no message should be a prefix of any other message. Otherwise, if you have something like what is given in option D, then if your source transmits 0001, then you won't know whether you have to consider this as 00 as being 00 and 01 being transmitted as messages, or is it 0001? So, which message is it that you're actually trying to encode? So, it's not very clear in this situation. That's why you need to have the condition that no message is a prefix of a longer message. That is, if your source transmits 0001, then when you try to do encoding, should you encode a 00 to some code word and then 01 to some code word, or should you encode each of the zeros to one code word and the final one to a code word? Or should you encode 00 separately to code words and then 01, since that's also a valid message? Should you encode this to, should you encode these three messages? So it's not very clear how to split your information sequence into message messages from your message set. And the second question is, let zi equals xi comma yi, and assume that z1 z2 up to zn be IID samples from a joint distribution pz, by definition pxy, then as n approaches infinity, what is the value of product of px of xi, py of yi by pz of zi power 1 over n? And the options are, is it 1, 2 power minus h of xy, 2 power minus I of xy, or none of the above? Try it yourself. I'll come back and give the answer in 2 minutes. what we can do here is write the product term as a power by taking logarithm to base 2 and since you have a sequence of IID random variables, this summation I 1 to n divided by n will go to the expected value with probability 1. But this expected value is by definition minus I of xy. So minus of this expected value is mutual information. Therefore, the original product goes to 2 power minus I of xy with probability 1. Question 3. Which of the following statements is true? First statement, if a code is uniquely decodable, then it is also prefix free. If a sequence of lengths L1, L2 up to Ln for finite n satisfy Kraft's inequality, then it is possible that a prefix free code with these lengths may not exist. One can use Chebyshev inequality for Cauchy distribution to show that empirical mean is close to true mean. D is none of the above. Solution is option D. Option A says if a code is uniquely decodable, then it is also a prefix-free code. A prefix-free code is uniquely decodable, but doesn't necessarily mean if a code is uniquely decodable, it has to be a prefix-free code. Then the second statement says if some lengths satisfy Kraft's inequality, then we might not get a prefix-free code, which is also false because last week we showed the construction for getting a prefix-free code as long as the lengths satisfy Kraft's inequality. And similarly, the third statement is also false. So none of these are true statements. For more explanation, you will just have to go back and see the lecture videos. Next question for a ternary source with P equals 3 by 6, 2 by 6, 1 by 6. Develop, install tree with 7 terminal nodes and calculate entropy of distribution on terminal nodes. Uh, Let me write down the reasons for the statements being false in the previous question. So for A, the statement A was false because prefix-free codes are uniquely decodable, but the reverse may not be true. Can go see uh, week 2, lecture 1. B is false because Kraft's inequality is an existence condition which guarantees the existence of a code as long as the inequality is satisfied. C is false because Chebyshev inequality requires finite variance to use it, but the Cauchy distribution has infinite variance. So to form a tensile tree, uh, this is a ternary source, so K is 3, and the number of messages in the proper message set is given to be 7 because there are 7 terminal nodes. From that, but M must be equal to K plus Q into K minus 1. So 7 equals 3 plus 2Q. 2Q is 4 or Q is 2. So we have to extend a node twice. you have to go back and check how Tunstall's algorithm is carried out. We form the carry routed tree by extending nodes in each stage. That is, if you have a leaf with probability p, then you'll make turn it into a node and draw k branches from that leaf. So you have to, in each stage, extend the most likely leaf. Initially, you have one leaf or root with probability 1. Then you extend this into 3 leaves because it's a ternary source. Each of them corresponds to a message with probabilities. This has probability 3/6, this has 2/6, this has 1/6. Then you have to extend it once again. So that's the root extension. After you extend the root, you have to again extend the most likely leaf q number of times. So each time you do that, you are removing one leaf and adding uh, k number of leaves again. So in total, you are increasing the number of leaves by k minus 1. If you do that q times, then the total number of leaves you have is q into k minus 1. But uh, you initially have k leaves extending from the root node. So at the end of the algorithm, you will be left with k plus q into q minus 1 leaves, which correspond to the number of messages. So the number of messages is k plus q into k minus 1. So initially you have the root with probability 1 and you extend that to get 3 leaves, k leaves. In this case, k is 3. Now you extend the most likely leaf uh, q number of times. So there are q stages. Since q is 2, you have to do this twice. So first we extend 3/6 is the most likely leaf. So we extend the leaf 3/6, make it into a node. Now the probability of these new leaves is the probability of the node you extended, or the leaf you extended, into the probability of each of the source messages. Uh, to ex- to make the explanation clearer, suppose you have 3 uh, alphabets A, B, C. and that is your source. Then you have, if you only collect a single output from the DMS, then each of those is a message. So you have three messages ABC. Now by extending this leaf node for A, you get three more messages, and those are AA, AB, and AC. So what is the probability of the message AA? It is the probability that you get A as your first uh, source of output, or first source symbol, and A as your second source symbol. So it's P of A into P of A, which is 3 by 6 into 3 by 6, 9 over 16. What is the probability of getting the message AB? It is probability of getting the message A and followed by probability of getting B. And this is because this is a discrete memory-less source. If there was memory, it would be different. P of A comma B is just P of A into P of B. So P of AB is 3 over 6 into 2 over 6, which is 6 over, sorry, this is not 16, it is 36. This is 9 over 36, this is 6 over 36. Finally, P of AC is P of A into P of C, which is 3 over 36. Probability of B is 2 over 6, probability of C is 1 over 6. Now, since Q is 2, we have to do this process twice. We already done it once. Now again, one more time, we have to extend the most likely. For that, we have to figure out which of these is the highest probability leaf. 9 over 36 is, let me bring out my calculator and find out. 9 over 36 is 1 over 4, which is 0.25. 6 over 36 is 1 over 6, which is 0.1667, recurring 1666. I'll write it as 0.17. 3 over 36 is 1 over 12, which is 0.08. 2 over 6 is 0.33. 1 over 6 is 0.17. So the most likely 2 over 6 is the most likely leaf. So we extend the node corresponding to that probability, which is node B. Now the probability of B is probability of B into probability of A, which is 2 over 6 into 3 over 6, 6 over 36. Probability of BB is 4 by 36. Probability of BC is 2 over 36. Finally, you have this leaf C, which has probability 1 over 6. So the message set and corresponding probabilities are AA, AB, AC, BA, BB, BC, and C. So you have 7 messages. The probabilities 9 by 36, 6 by 36, 3 by 36, 6 by 36, 4 by 36, 2 by 36, and 1 over 6. 1 over 6 can also be written as 6 over 36. Now, the average depth is we have 3 branches of depth 2 stemming from A. So AA, B, AC are of depth 2, and the probabilities are 9 by 36, 6 by 36, and 3 by 36. We have 3 more branches of depth 2 whose probabilities are 6 by 36, 4 by 36, and 2 by 36. And we have a branch of depth 1 whose probability is 1 over 6. This is 2 times 3 over 6 plus 2 times 2 over 6 plus 1 times 1 over 6, which is 11 over 6. That's the average depth. The entropy of the nodes is 3 over 6 log 6 over 3 plus 2 over 6 log 6 over 2 plus 1 over 6 log 6 over 1, which is half plus log 3 divided by log 3 divided by 3 plus 1 by 6. Now the leaf entropy is average depth into node entropy, which is 11 by 9 plus slight correction here. So we can split the final term as log of 3 into 2 divided by 6. which can be written as log 3 by 6 plus log 2 by 6. Log 3 by 6. Uh, so we already had a, let me write that again. 3 over 6 is half. Log of 6 over 3 is log 2. So log 2 to base 2 is 1. That's why we have a half. Then we will keep it as it is. 2 over 6 logs. 6 over 2 is 3 to base 2. Then 1 over 6, we can write that as 1 over 6 log 3 plus 1 over 6 log 2. The 6 is 3 into 2. This is 1 over 6 log 3 base 2 plus 1 over 6 log 2 base 2. But log 2 base 2 is 1. Therefore, it's just 1 over 6. Now 2 over 6 log 3 plus 1 over 6 log 3 is nothing but 3 over 6 log 3, which is half log 3. And half plus 1 over 6 is nothing but uh, 4 6, which is 2 thirds. That's why we have 2 thirds plus half log 3. Now average depth is 11 by 6 into 2 by 3 plus half log 3 will give you 11 by 9 plus 11 by 12 log 3, which is option A. Question 5. Which of the following is likely to be a typical sequence coming out of a source with probability of u equals 0 is 0.25, probability of u equals 1 is 0.75, for length L equal to 32. By definition of a typical sequence, in an epsilon typical sequence, we have the number of times the symbol A occurs divided by the number of length of the sequence is between 1 minus epsilon, the probability of that symbol, and 1 plus epsilon, the probability of that symbol. So here there are only two symbols, 0 or 1. So n of 0 is the number of zeros and n of 1 is the number of ones. So n of 0 divided by 32 is between probability of getting 0, which is 0.25, into 1 minus epsilon less than or equal to 1 plus epsilon into 0.25. And n of 1 divided by 32 is between 1 minus epsilon 0.575 and 1 plus epsilon 0.75, which implies n0 is 1 minus epsilon times is between 1 minus epsilon times 8 and 1 plus epsilon times 8, and n1 is between 1 minus epsilon times 24 and 1 plus epsilon times 24. So you have approximately 8 zeros and 24 ones. So you should check among the four options which of these uh, sequences follow satisfies that condition. Can straight away rule out option B because it is a sequence of all ones, so it's not a typical sequence. Option A has, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Already it's more than 8 zeros, much more than 8 zeros. So that's not a typical sequence. You need about 8. Uh, it should be around 8 zeros. Depending on epsilon, it could be. If epsilon is point point 1, say you would have point 0.9 into 8, which is 7.2, and 1.1 into 8.8. If it's a little less than point 0.1, then you would have between 7 and 9. So for small values of epsilon, very small values of epsilon, it should be exactly 8. For relatively small values, around zero point 0.1, it should be between 7 and 9. So it definitely can be option 1 where there are much, much more than 9 zeros. Similarly, it can be option C. Either option C has, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 zeros is too much. Suppose n of A or n of 0 is 16, then you would have half less than or equal to 1 plus epsilon 1 over 4. This should mean 1 and greater than or equal to 1 minus epsilon 1 over 4, which would mean 1 plus epsilon 1 minus epsilon is less than or equal to 2, and 1 plus epsilon is greater than or equal to 2, which would mean epsilon is greater than or equal to 1, which is a pretty high value. So when we write 1 minus epsilon, 1 plus epsilon, the epsilon should be small relative to 1. So it should be typically it should be at least 10% of uh, the number you are subtracting from. From that we can see that option D is the typical is most likely to be the typical set. It has, let's see, 1, 2, 3, 4, 5, 6, 7, 8 zeros and 24 ones, which was exactly what we were looking for. Let x be a random variable such that x takes the value is 0, it takes the value 0 with probability 1/4, x takes the value 1 with probability half, and x takes the value 2 with probability 1/4. Let Zn be the product of n such random variables x1, x2, which are all distributed independently and identically with the probability distribution of x. Then h of Zn as n approaches infinity is what? Is it 1, 0, infinity, or 2? We have probability of Zn not being equal to 0 is 1 minus. So uh, to find the entropy of h of Zn, we must first know what are the values that Zn can take, and then the probability that Zn takes those values. So first thing is Zn can take the value 0 if any one of the xi's in x1 to xn is 0. So Zn does not take the value 0 with if and only if each of the xi's does not take the value 0, and each xi does not take the value 0 with probability 1 minus 1 by 4, just 3 by 4. Because the probability that xi takes value 0 is 1 by 4. Probability that xi does not take the value 0 is 3 by 4. Probability is that none of the n xi's takes the value 0 is 3 by 4 power n. The probability that Zn is not equal to 0 is equal to 3 by 4 whole power n. So as approaches infinity, probability that Zn not equal to 0 approaches 0 because 3 by 4 is a number less than 1. So with high probability, Zn is equal to 0. That means uh, as n increases, Zn becomes more and more deterministic. So this means that probability of Zn equal to 0 approaches 1. So the uncertainty h of Zn approaches 0. And that's just an informal way of writing it. Formally, we would write it as follows: h of Zn is minus probability Zn equals 0 log of probability Zn equals 0 minus summation over all I probability that Zn equals I log of probability that Zn equals I, where if Zn uh, equals I, where I not equal to 0, because we have already taken care of Zn equals 0. So if I not equal to 0, each of the xi's takes either the value 1 or 2. For each particular value that an xi takes, for all I equals 1 to n, maybe I should write this as some other variable k, so you're not confused. So if um, n equals 2, let's say, then z equals x1, x2. So x1, x2 can x1 can take the value 1, 2, and x2 can take the value 1 or 2. So x1, x2 can take the value 1, 2, or 4. There are three non-zero values that z can take. Similarly, z can take that is x1, x2, x3. Then each of these can be 1 or 2. So you can get you can get 1 into 1 into 1, which is 1, or you can get 1 into 1 into 2, which is 2, or you can get 1 into 2, which is 4, or you can get 2 into 2 into 2, which is 8. You can get any of these four values. So for this summation, second summation is for all non-zero values, overall non-zero values k that Zn can take. Now this is less than or equal to minus PR of probability of Zn equals 0 log probability of Zn equals 0 minus, so each of these probabilities. So the lowest probability sequence in this n-length sequence. In this summation, this is the summation over all n-length sequences uh, where each of the x's does not take a 0. So all n-length sequences where each of the variables is 1 or 2. Among all those sequences, the lowest probability sequence is a sequence of all 2's, because 2 occurs with the probability 1 by 4 and 1 occurs with probability half. So the least likely outcome is a sequence of all 2's, uh, as long as given that the value 0 does not occur. That's the lowest probability, and since we are taking the negative of those probabilities, uh, the second sum here is less than or equal to log of probability of Zn equals 2 power n summation probability of Zn equals k over all k is that k not equal to 0. That is for every sequence, for every other value other than 2 power n, the probability of that value is larger than, in other words, PR of Zn equals k greater than or equal to probability that Zn equals 2 power n for all k not equal to 2 power n. Therefore, the negative of that probability Zn equals k is less than or equal to negative value of probability Zn equals 2 power n for all k not equal to 2 power n. So each of these log values is less than or equal to log of probability Zn equals to 2 power n. So I take out the log value, I get an inequality, an upper bound, and the probability that Zn is equal to 2 power n is 1 over 4 power n, because each of the xi is a IID, and the probability that xi is equal to 2 is 1 over 4. So this is minus probability Zn equals 0 log of probability Zn equals 0 minus log of 1 over 4 power n summation of all probabilities Zn is equal to k such that k is not equal to 0 uh, is nothing but probability that Zn not equal to 0. So this is equal to minus probability Zn equals 0 log of probability that Zn is equal to 0 plus 2n into 3 by 4 power n. As n approaches infinity, probability that Zn equals 0 approaches 1, and 2n into 3 over 4 power n approaches 0. Therefore, h of Zn approaches minus 1 log 1 plus 0, which is equal to 0, which is option B. Again, it's the same thing. X is a random variable such that x is 1 with probability 1 over 4, 2 with probability half, 4 with probability 1 over 4. And instead of taking 0 and 2, it's taking 1, 2, 4. And Zn is uh, nth root of the products where x1, x2, xn are IID distributed as px. Then as n approaches infinity, Zn converges to, so it converges to 1, infinity, 0.75 or 2. We have Zn is 2 power 1 over n summation log xi is equal to 1 to n by strong law of large numbers. This quantity log of Zn is equal to 1 over n summation log of xi is equal to 1 to n converges to expected value of log x. So this 1 over n summation log of xi is equal to 1 to n is the sample mean of log of xi. So if you consider log of xi as some other random variable yi, and if you consider there are n such random variables, or if you consider a single experimented distributed according to the distribution of x, um, repeated n times. So you have n samples and you take the sample mean. Here you are not directly taking the sample mean, you are taking the sample mean of the log of the random variable. Then the sample mean converges to the expected value. That's what the strong law of large numbers says. That is, suppose you have a random variable x. Suppose you have an experiment, and to the outcomes of the experiment, you have assigned a random variable. Let's just say you have a one-to-one mapping between the outcomes and the value of the random variable. So x is a one-to-one mapping. Then you don't really know if you don't really know the distribution of x or the distribution of the experiment, then you can conduct n trials of that experiment and find out the values of the random variables in those n trials, sum all those up and divided by n. So that's your sample mean. So if you conduct enough number of such experiments, that is, if n tends to infinity, then you should uh, the sample mean should get closer and closer to the actual mean value according to the actual distribution that x has. That is one of the reasons why we can think of uh, the probability of uh, when we say the probability of a coin toss is half, we would think that if you toss the coin 1,000 times, then 500 times you will get heads and 500 times you will get tails, approximately. And if you get to toss it 10,000 times, then it will the number of heads will get closer and closer to half of the number of tosses. But when we actually write out the probability distributions, it's just an axiomatic definition. It doesn't really have a correspondence with what is happening in reality. Doesn't really have to be that way. So these laws of large numbers give you a kind of an idea of a bridge between the intuitive notion of probability as a likelihood when you conduct a large number of experiments and the axiomatic notion of probability that just talks in terms of probability distribution. Okay, now we have this is with probability 1. When we say it's with probability 1, what it means is that the sample means 1 over n log of xi I equal to 1 to n minus the actual mean expected value of log x is less than some quantity epsilon uh, with probability 1 minus delta or something, where delta is a small number that can be made arbitrarily small. Now we have for this experiment expected value of log x is 1 by 4 log 1 plus half log 2 plus 1 by 4 log 4 is 1. Therefore, Zn is 2 power e to the log x. It's 2 power 1, which is 2. As n approaches infinity, probability 1, which is option D. Question 8. You have been asked to encode a sequence of symbols that come from an alphabet with D symbols. You will have to encode symbols A1, A2, and A3 using code words that are 3 bits long. You will have to encode symbols A4, A5 up to AD, using code words that are 4 bits long. What is the maximum value of D for which this is possible if the code must be uniquely decodable? So for uniquely decodable code words, code word lengths must satisfy the craft inequality. Therefore, we have first three code words have length 3 and the remaining code words have length 4. Should mean that d minus 3 by 16 is less than or equal to 5 by 8 or d less than or equal to 13. So max value of d is 13. Forgot to give you the options. Options are 13, 10, 11, and 8. So the right answer is option A. Question 9. Let Xn be a stationary, finite alphabet stochastic process. Let n greater than or equal to 2. Then which of the following is true? H of xn plus 1 comma xn given x0 x1 is equal to h of x0 x1 given xn plus 1 comma xn. Is it equal to or is it less than or equal to or is it greater than or equal to? We have h of x0 x1 up to xn, sorry, x0 x1 xn plus 1 comma xn is equal to h of x0 x1 plus h of xn plus 1 comma xn given x0 x1, and this is also equal to h of xn plus 1 xn plus h of x0 x1 given xn plus 1. So by the stationarity of the stochastic process, h of x0 x1 is equal to h of xn plus 1 xn, which implies h of x0 x1 given xn plus 1 xn is equal to h of xn plus 1 xn given x0 x1, which is option A. Final question. Let x0 x1 etc. xn form a Markov chain. Which of the following is true? From the data processing inequality, we have I of x0 xn minus 1 is greater than or equal to I of x0 xn, which implies h of x0 minus h of x0 given xn minus 1 greater than or equal to h of x0 minus h of x0 given xn, which further implies so this implies h of x0 given xn minus 1 is less than or equal to h of x0 given xn. That is, as you condition on a Random variables that is more and more downstream, the uncertainty in x0 grows. It can only go up, can't go down. And compared to conditioning on a random variable that is uh, to the left, that is more upstream. That is x1 contains more information, or knowing x1 will reduce the entropy in x0 more than any of x2, x3, up to xn reduce the entropy in x0. You can say this is a more generalized version of this is the entropy version of the data processing inequality. Answer is option B. That's all for today. See you in the next session.